Yes, Abdullah. In which part you have doubts?
The B part and E part.
See, Abdullah, in part B, is asking whether what purpose this 600 kilo ohm resistor do. So the point for asking this question is because near the null point, no current flows through this resistor. Near the null point, no current is flowing through the resistor. Then why this resistor is here if there is no current is flowing through it in the circuit, right? So first thing is this 600 kilo ohm resistor will not affect balancing length. The reason why this 600 kilo ohm resistor will not affect the balancing length is because when you get the balancing length, that means your galvanometer is connected to the null point. When it is connected to the null point, then galvanometer current is zero, no current through the galvanometer. If no current is flowing through the galvanometer, then this resistor cannot affect your circuit. Resistor can only affect your circuit if some current is flowing through it. So first of all, this 600 kilo ohm will not affect the balancing length. It will not affect the null point. The reason is at the null point, current in the circuit is zero. Abdullah, is this thing clear? Then I will tell you the purpose of 600 kilo ohm.
Yes, sir. Yes, sir. I got it.
Now, if it is not affecting the balancing length, then why we are using it in the circuit? The reason is you never get the null point in a single attempt. What we do, we take this galvanometer, we put jockey here, then we put the jockey here, then we put jockey here, when we put jockey. When I put jockey here, when I connect galvanometer to this point of the potentiometer, what is the current through the galvanometer, Abdullah? Is it zero or non-zero?
Non-zero.
Non-zero. When the current is non-zero, that means some current is flowing through the circuit.
Yes, sir.
That current is very large. That current can damage your potentiometer wire, or that current can damage your galvanometer. Very large current that can damage your galvanometer. So to decrease that current, we use this high resistance. So we use this high resistance to decrease current. Decrease current. So that it doesn't damage your galvanometer.
Galvanometer or potentiometer?
Both. Galvanometer and your circuit. Okay. Now,
Yes, sir.
so and when it could damage the galvanometer, when balancing length is not obtained, when null point is not obtained. Null point isn't obtained. This is the purpose of using high resistance. Yes, next, which part, Abdullah?
Sir, E part.
E. Would the method work in the above situation if the driver's cell of the potentiometer had an EMF of 1 volt instead of 2?
No, sorry, sir. F part, sir. Sir, F. Sir, actually,
Would,
in the new textbook, it's only till E. So
okay.
my E part is F part over
Okay.
there.
Would the circuit work well for determining an extremely small EMF, say order of a few millivolt? See, to measure extremely small resistance, what we do is we decrease K. To measure extremely small voltage, to measure extremely small voltage, extremely small voltage, we decrease K. Gradient, will decrease the value of gradient. See, how can you decrease the value of gradient? Gradient is this now, driving cell by R plus R multiplied by small r divided by L. You can decrease the value of K by various methods. You can increase this resistance R. This resistance here is external resistance R. By increasing R, you can decrease the value of gradient. Or what you can do is you can increase the balancing length. So not balancing length, the length of the potentiometer wire. If you increase the length of the potentiometer wire, then also your K will decrease. So the F part says, is this circuit suitable for using extremely small voltage? No. For using extremely small voltage, K should be very small. So you have to decrease K. How would you decrease K? K depends upon R and capital L inversely. So if you can increase R somehow, or you can decrease K, then if you can increase R, then your K will decrease. If you can increase the length of the potentiometer wire, this whole length, instead of some, let's say 1 meter wire, you are using 100-meter wire. If you increase L, then K will decrease. Yes, Abdullah. I hope it's clear now.
So, sir, it's not suitable basically.
But see, yes and no are not the answers in physics. The answer is why. It's not suitable, but why it's not suitable? Because its K is very small. You have to decrease the value.
Okay, sir.
So these two questions are very important. This, at least this 3.22 is very important of for current electricity. In 3.22, you may not get this numerical, but you can get these conceptual questions from E to F. And then there is one more important question here. I'm just marking it out. Yeah, this question number A of 3.18. That's important. Question number A, part A of 3.18. That's very important. That's it. Aji, can I change this right now? Any other doubt?
So, which question is that? 3 point?
3.18 part A.
Okay. Okay, sir.
Okay. Yes, no. So Noor, part F says, would the circuit work well for determining an extremely small EMF, say of the order of few millivolt? That is of a term couple. If not, how will you modify the circuit? See, this circuit that you are using is for a cell of some high voltage. Like the EMF of the cell, it comes out to be around 1 or 1.2 volt. The potentiometer circuit, let's say the EMF of the cell is some 1.2. So the potentiometer circuit that you are using to measure EMF of 1.2 volt is not suitable to measure EMF of, let's say, 10 raised to the power minus 3 volt. If you want to measure this small EMF, then you have to decrease the value of potential gradient. So the first part is it suitable? No, it's not suitable. How will you make it suitable? You will decrease the value of K. And how would you decrease the value of K? Say K depends upon E by R plus R into small r by L. So K depends upon capital R and L inversely. So if you can increase R, your K will decrease. If you can increase L, then your K will decrease. So potential gradient will decrease on increasing the resistance. Potential gradient will decrease on increasing the length of the potential. Yes, Noor. Clear now?
Yes, sir. My doubt is clear.
So that was about circuits. There is one more small topic not given in NCRT, but we have already discussed this topic, but I just want to discuss few questions on it. Heating effect of current. Heating effect of current. After this topic, we'll be starting with magnetics. So whenever current passes through a resistor, it heats it up. When current passes through a resistor, the resistor gets heated up. It's basically what happened is some part of electrical energy gets converted into heat. That is known as heating effect of current. So part of when current pass through a resistor, part of electrical energy, part of electrical energy is dissipated as heat. This is the heating effect of current. So heat dissipated per unit time is power. Heat dissipated per unit time is power. So this is also known as power dissipated. So power is nothing but heat divided by time. The expression of power we have already used. We can use three expressions for power dissipated: I square R, or it's V square by R, or it's V into R. These are the three expressions of power that we use. Next, if you want to calculate heat, then heat is simply power multiplied by time. SI unit of power is what? Power is what? But usually, when we talk about electricity, we measure power in kilowatt. So practical unit is kilowatt. That's the practical unit of power, kilowatt. So whenever heat energy passes through anything, it part of electrical energy when electrical energy passes through a resistor, a part of electrical energy dissipate as heat, which is known as heat energy. Or power dissipated as heat is the expression for power. If you want to calculate heat, then you can just multiply power with time. On this concept, you get question on bulb. I'm discussing few questions on bulb. Say if you take I'm giving you example. An electric bulb of have voltage and power reading as 100 volt and 200 watt. 100 volt and 200 watt. So this 100 volt is the voltage rating of the bulb and 200 watt is the power rating of the bulb. You're supposed to calculate first part, resistance of the bulb, second, power dissipated if it is connected to source of 50 volt, third, power dissipated if it is connected to source of 120 volt. So these are the three parts of the question. So first of all, see what do you mean by power rating and voltage rating of the bulb. So not just bulb, if you take any device, say you take a CFL. On the CFL, it's written like this is 10 volt, 100 watt. You take a bulb or CFL or any other device, on the wrap over the CFL, the rating is written. It's written it's 10 volt, 100 watt. That means if you connect this bulb or this CFL with a cell of 10 volt or a supply of 10 volt, it will generate a power of 100. This 10 volts bulb can generate a power of up to 100 watt. So this is the voltage rating and this is the power rating. So here the voltage rating is 100 volt and power rating is 200 volt. These are the voltages and power for which the bulb is designed. This bulb is designed that if you connect it to a source of 100 volt, it will generate power of 200. First part. You're supposed to calculate the resistance. You can write power rating as V naught square by R. P naught is the power rating, V naught is the voltage rating. So from here, you can write that your resistance as V naught square divided by P naught. You can write your resistance as 100 square divided by 200. So this is 1000 by 200 gets cancelled out. So it comes out to be, sorry, I should write more steps. So it's 100 square divided by 200. So that's 10 raised power 4, 100 by 2, which comes out to be 50 ohm. So that's the resistance of the bulb. Is it clear?
Yes, sir.
Voltage rating and power rating is simply the voltages and power for which the bulb is designed. Say if you go to market, you bring a bulb, or the bulb is written, it's 20 volt, 200 watt. Means if you connect this bulb to a supply of 20 volt, it will generate a power, a brightness corresponding to 200 watt. The second says, if it is connected to a source of 50 volt, this is the applied voltage, which is 50 volt. What do you think, Fatima? The power dissipated would be 200 watt, more than 200 watt, or less than 200 watt if we connect this bulb to a 50 volt cell, 50 volt source? Fatima, if I connect this bulb to a source of 100 volt, it generates a power of 200 watt. The resistance of the bulb is 50 ohm. Now I'm asking, if I connect the same bulb to a 50 volt source, will it generate a power of 200 watt or less or more than that?
Less.
Less. It will generate less power. Now the question is, how will you calculate that power? So for power dissipated, you can use the simple relation P is V square by R, right? Instead of V naught, you will use V. So you will use 50 square divided by 50. Is it clear? So I should write on this. P V square by R. So P will be V square, means 50 square divided by 50. So it comes out to be 50 watt. So this is the 50 watt. Clear?
Yes, sir.
One more thing. What if you connect this bulb to 120 volt supply? You brought a bulb of 100 volt from the market and you connect it to a source of 120 volt. What will happen with the bulb? Yes,
It will
yes,
break.
it will fuse, it will break. Yes. V is greater than V naught. Applied voltage is greater than voltage rating. It's greater than voltage rating. Voltage rating. Bulb will get fused. So you cannot connect a device to a voltage which is greater than its voltage rating. Voltage rating means this is the maximum voltage that you should apply to this device. This is the last topic. Next, homework. You will write short note on nichrome, on these type of wires, constant time. You should write short notes on these two wires. You can get theoretical questions on them. Note it down. We'll do few questions from previous years and we'll start magnetics. Tell me once you have written. Yes, can I change the slide now?
Yes, sir.
We'll discuss two numericals on this concept.
So what is this?
Okay. Constant time. This is a type of alloy.
Okay. Done, sir.
Okay. Okay, let's do few conceptual questions on heating effect. One conceptual question and one numerical. So the first conceptual question is, under what condition is the heat produced in electric circuit first directly proportional to resistance? And write your answers in chat room. Huh? Second, inversely
Sir, is this like MCQ?
proportional to resistance. Yes, Abdullah?
Is this like a MCQ? We have to choose the correct answer.
No, you just have to write the answer. Not MCQ. Two questions. Part one, when heat is directly proportional to resistance and when heat is inversely proportional to resistance. Write it down. This was in CBSE sample papers, very old sample papers, 2004. This was given in CBSE sample paper. Answers? See, this is straight conceptual question. Yes, no, first part is correct. Good. Good, Noor. See, first part. You need when heat is proportional to resistance. So, see, we have three expressions for heat, right? One is I square R, another is V square R, another is VI. This is not useful because resistance is not given in this expression. So we'll be using the first two expressions, I square R and V square R. So if in this expression I say current is constant, if I is constant, that means power is directly proportional to resistance. So in the first part, when the question says that when is heat directly proportional to resistance, you can write heat power dissipated is I square R. If I is equal to constant, if current is constant, then P is directly proportional to R. So when is heat directly proportional to resistance? When current is constant. Yes, Abdullah, second is correct. You also have P is V square by R. If V is constant, then your power is inversely proportional to resistance. So greater the resistance, smaller would be the power. Is it clear? Mariam?
Yes, sir.
Okay, let's do one more numerical. One more numerical on the same concept of power. See, next question. Three identical resistors, each of resistance R, when connected in series, when connected in series with DC source, dissipate power X if resistors are connected in parallel to same DC source, how much power will be dissipated? Okay, Abdullah, it's present prayer time. Let's have a break of 7 minutes. We'll continue at 10:03, 10:04, 9:12, 9:30. Na? After 5 to 7 minutes, we'll meet. So let's solve this numerical. You have three identical resistors, each of resistance R. When connected in series with a DC source, dissipate some power X. So if your resistors are connected in series, so your equivalent resistance is R plus R plus R equal to 3R. When you connect it to a voltage source, the expression of power becomes its V square divided by R equivalent. Power is given as X, the expression of power is X. So it's V square divided by R equivalent. Here R equivalent is 3R. So from here, you can get the value of V square. Your V square becomes 3R multiplied by X. Now I call this as equation. So when they are connected in series, the power dissipated is X. The voltage square can be written as 3Rx. You're supposed to calculate power dissipated when they are connected in parallel. When the resistors are connected in parallel, then you can calculate R equivalent in this way. 1 by R equivalent is 1 by R plus 1 by R plus 1 by R. Your R equivalent will become 3 by R. So you can write that R equivalent is R by 3 now. This is your R equivalent, which is R by 3. So if you have R equivalent and you have voltage, you can easily calculate your power dissipated. Now the power dissipated is V square by R equivalent. I call this as equation number 2. I call this as equation number 3. In this equation number 3, you can substitute the value of V square because voltage was not given. Voltage we calculated using the series case. So next we can substitute 1 and 2 and 3. When we substitute 1 and 3 and 2 and 3, we get power as 3 times Rx divided by R by 3. R gets cancelled with this R. This 3 will go to numerator and your power becomes 3 into 3x, that's 9x. So as compared to series, if you connect resistors in parallel, then your power will become 9 times. So earlier you have connected resistors in series and the power was X. When you connected the same resistors in parallel, the power becomes 9x. Yes, is it clear?
Yes, sir.
Sure. Let's note it down. That was the last question on current electricity. There is one more topic in current electricity, and that is color code of carbon resistor, but that's not a part of syllabus now. So I'm not discussing that topic here. Yes, can I change the slide now?
Yes, sir.
Mariam, you can take screenshot if you want.
Yes, sir.
Or just note this numerical, right? Note the solution. It will take hardly 1 minute. Just note it down. Okay, let's change the slide. Next is unit number 3. Magnetics and magnetism. See, magnetics and magnetism actually have, there are two topics in magnetics and magnetism. This includes chapter number 4 and 5 of NCRT. NCRT chapter 4 and 5. 4 is a bit lengthy, but 5 is won't take more than 1 or 2 lectures. 5 is very small. So this includes two topics. One is magnetic effect of current. Magnetic, that's a lengthy topic. Magnetic effect of current. Another is natural magnetism. Another is natural magnetism. So these are the two topics that we'll be discussing. This is chapter 3 and this one is chapter 4. So this magnetic effect of current magnetic effect of current. This starts with the concept of magnetic field. In the next 3 chapters, we will be discussing magnetic field in very much details. The way we have used electric field, the last 3 chapters, chapter number 1, chapter number 2, chapter number 3, all were related to electric field directly or indirectly. In the same way, chapter 4, chapter 5, chapter 6, they are connected directly to magnetic field. We'll be discussing daily. In every lecture, we'll be discussing magnetic field. So what is magnetic field? Just like electric field, magnetic field is a space around a magnet in which its magnetic properties exist. If you have a magnet, we will discuss what's a magnet basically, what do we mean by magnet. But if you have a magnet, let's say you take a bar magnet which have north pole and south pole, then the space around the magnet which will have a field, and that is known as magnetic field. Space around a magnet. Space around a magnet where its magnetic properties exist. Magnetic properties exist is magnetic. So if I take a magnet, a north pole and a south pole, then around this magnet, a certain lines, there's a region where the magnetic properties of this magnet can exist. This region is magnetic field. Magnetic field is not a physical quantity here. It's just the name of a region where the magnetic influence of this magnet can exist. Magnetic influence exists means if I take another magnet, then this magnet can attract or repel the another magnet. That space is magnetic. Now, if I want to measure the strength of magnetic field, like how strong the magnetic field is at a particular point, then we use certain terms which are known as magnetic field strength, magnetic field strength, or you can say magnetic field intensity, or you can say magnetic flux density. The same thing. Magnetic flux density. If you remember electric field, then electric field also had the same construction. We first studied electric field, that what is electric field? Space around a charge. Then we studied how we measure field. When we measure field, then we use terms like electric field strength, electric field intensity, electric flux density. And casually, we never write electric field intensity, we always write electric field. But we know when we are writing electric field, we know that we are talking about electric field intensity, the quantity that can be measured. In the same way, we always measure electric field intensity or electric field strength, but we casually call it we always measure magnetic field strength or magnetic field intensity. But casually, we call magnetic field strength as magnetic field only. Although magnetic field is not a physical quantity, magnetic field is just a space around a magnet. The strength of that space, that magnetic property is magnetic field strength. But casually, we call magnetic field strength as magnetic field. This is strength of magnetic field, nothing else. Strength of magnetic. The strength of magnetic field is represented by B. Strength of magnetic field is represented by SI unit is Tesla. Capital T. CGS unit is Gauss. CGS unit is Gauss. 1 Tesla is 10 raised to the power 4 Gauss. So that's the relation between Tesla and Gauss. 1 Tesla is 10 raised to the power 4 Gauss. CGS unit. So now we know what is magnetic field, what is magnetic field strength. The next is sources of magnetic field. What are the different sources of magnetic field? If you start thinking about the sources of magnetic field, you can come across these sources. First is current carrying wire. If you have a current carrying wire, then that current carrying wire can generate magnetic field. Apart from current carrying wire, you can think of a bar magnet. You can think of a horseshoe magnet. You can think about an electron. Even a revolving electron generates magnetic field. But if you start classifying all these sources, a straight wire having current generates magnetic field. That magnetic field arises due to current. If you take a bar magnet, even inside a bar magnet, some current is flowing and that current is generating magnetic field. Again here, in the case of bar magnet, the source is current again, because at the north pole, at the south pole, electrons are revolving, and revolving electrons are nothing but current. So even in a bar magnet, it's current associated with a revolving electron, which generates magnetic field. Instead of bar magnet, if you're using horseshoe magnet, the same story. Even in a horseshoe magnet, there are revolving electrons, and those revolving electrons will generate magnetic field. So horseshoe magnet, bar magnet, solenoid, toroid, current carrying wire, they all have current in common. So current, electric current, electric current. Current carrying wire, current carrying wire. Or another example of electric current could be bar magnet. Or another example could be your solenoid. All these sources are nothing but electric current only. Do you know any other source else than current which can generate magnetic field? Have you heard about any other source than current? Yeah. Yes, Ahmed. Which one?
Friction.
Friction. No, Ahmed. Friction cannot generate.
Light.
Light consists of magnetic field, but you can't say that light is generating magnetic field. To be more precise, there are some special type of field in the light which is generating magnetic field, but not light. Light is not generating field, magnetic field. Any other source? Have you heard about spin? Electronic spin, plus half, minus half?
Yes, sir.
That spin of plus half and minus half basically represents the magnetic field generated by electronic spin. So one source is electric current, another source is spin. These are the intrinsic electronic spin. Intrinsic electronic spin. That plus half, minus half that you studied in chemistry. This plus half and minus half are sources of magnetic field only, nothing else. Just represent magnetic field only. So these are the sources of magnetic field. Out of these many sources, right now in this chapter, we will focus only on current carrying wire. Chapter number 3, focus solely on current carrying wire, nothing else. And the next chapter, focus on bar magnet, sources like bar magnet. That's it. You won't study intrinsic electronic spin in this year at least. Note that net current is zero. Net current is zero. It won't show that deflection. In fact, your galvanometer cannot show that small current which is flowing in the atom.
Okay, sir.
Not just your bar magnet. If I take this piece of conductor, it will have electrons. If that electrons are moving in one particular direction, then there must be current. But you cannot detect that current using a normal galvanometer. That current is too small to be detected by the galvanometer. Okay, so what we have to study, we are supposed to study the magnetic field of a straight current carrying wire. That's it. So the magnetic field of a straight current carrying wire, to measure or to calculate the magnetic field of a wire, we need a law. Just like for electric field, we have laws like Coulomb's law, and then we did a law like Gauss law. In magnetism, we have two laws. Somewhat like Coulomb's law, we have Biot-Savart's law. And there is one more law, Ampere-Circuital law, which look like Gauss law. So we're doing first Biot-Savart. They were father and son pairs. Biot was father, I guess. Savart was his son, or it's either way. So they gave a law to calculate magnetic field due to a current carrying element. They said if you have a wire, or you can have wire of any shape and size. I'm not drawing a straight wire, I'm drawing a wire which is curved from its ends. It could be a wire of any shape and size. This is if you take a current carrying wire, then consider a small portion of the wire, a very small portion, a small portion of length dl. Some current I is passing through the wire. They call this small element dl as current element. Extremely small element is current element. They said that Biot-Savart's law is valid only for this small current element only. By using Biot-Savart's law directly, you cannot calculate magnetic field due to a long wire. Like if I give you this wire, by using Biot's law, directly Biot's law, you cannot measure magnetic field of this wire. You cannot calculate magnetic field of this wire. To use Biot-Savart's law, you need a small current element. So if I give you this current carrying wire and I say this is generating some magnetic field, calculate the magnetic field of this wire. So what you will do is you will first consider a very small element of the wire. You will calculate the magnetic field of that small element, and then you will integrate it over the entire wire. This is how we calculate magnetic field due to long elements using Biot-Savart's law. But right now we'll focus on small elements only. The next section we will see how to extend it to large elements. So you have a wire. I consider a small current element of the wire. I take this as point P. We're supposed to calculate magnetic field at this point P. This separation is R. This angle is theta. So what we need magnetic field at P. Magnetic field at P due to current element dl. This is my small current element dl. This is generating some magnetic field that we will try to calculate. So according to Biot-Savart's law, this magnetic field dB is directly proportional to the current and current element. Like if you keep on increasing the value of current in the wire, then the strength of magnetic field here will increase. It's directly proportional to sine theta. See here, R is position vector of P. R is position vector of P. What is theta? It's angle between DL and R. The angle between DL and R is theta. Theta is angle between DL and position vector R. This separation. This is the small element. You want to calculate magnetic field at P. You connect that small element to P. This is the vector R. And this is the direction of DL. The angle between the DL and R is theta. So Biot says magnetic field is proportional to IDL. Magnetic field is proportional to sine theta. Magnetic field is inversely proportional to the square of distance between. If you combine all of these, you will get magnetic field is proportional to ideal sine theta over r square. Is it clear?
Yes, sir.
Yes, sir.
It's somewhat like Coulomb's law. In Coulomb's law, we were calculating force. We were calculating force due to a point charge only. Here, instead of point charge, you have a small element only. There also, your force was inversely proportional to r square. Here also, your magnetic field is inversely proportional to r square. Do you remember what happened when we removed the sign of proportionality in Coulomb's law? What constant we get? We got a constant, right, in Coulomb's law?
Coulomb's constant.
1/4
1 over 4 pi epsilon naught. We get absolute permittivity, right?
Yes, sir.
Here, and what absolute permittivity represent? Absolute permittivity shows the effect of medium on electric force. Like how medium is affecting electric force, how medium affect electric field was represented by epsilon naught, absolute permittivity. Here, instead of absolute permittivity, we will be using absolute permeability. So we'll write dB as it's mu naught by 4 pi ideal sine theta. So what is mu naught? Absolute permeability of free space. Just like permittivity, you have permeability here. So this permeability basically shows how medium affect magnetic field. This shows effect of medium on magnetic field. When we say free space, that means which medium is free space? When I say it's free space, it's air or vacuum.
Vacuum.
For air or vacuum, its value of mu naught is 4 pi into 10 raised to the power minus 7. The unit must be Newton meter per ampere. Tesla meter per ampere, right? Yes. So it's Tesla meter per ampere is mu naught. Now, instead of free space, if I'm using any other medium, do you remember in Coulomb's law, we use 1 over 4 pi epsilon naught. If I change medium, then what constant we use?
Four pi into k, and over here k will be something related to medium.
Sir. Sir.
Yes. Have you noted those uh, 3 slides, or I should write it again?
I noted.
Yes, sir.
Yeah.
Noted.
Noted all I have noted. Fatma, Mariam.
Yes, sir.
Sure. Okay, so I should repeat with Bard's if it's wrong. Yeah. So, so reading Bard's if it's wrong. Biot's if it's wrong. Just one second. Biot's if it's wrong. So DL is current element. Current element. R is position vector. I'm just coming to that point. First, let me write. R is position vector. Theta is angle between R and P. Of point P. We need magnetic field at P. Magnetic field at P due to current element DL. This magnetic field is proportional to ideal. It's proportional to sine theta, is inversely proportional to R square. So we can write this as proportional to ideal sine theta by R square. So when I remove the sign of proportionality, we use constant mu naught. Ideal sine theta by R square. Where mu naught is absolute permeability of free space. The value of mu naught is 4 pi into 10 raised to the power minus 7 Tesla meter per ampere. Now, if we change, and this absolute permittivity of free space shows effect of medium on magnetic field. Medium on magnetic field. In electrostat, when we change medium, we were using dielectric constant. Here, when we change medium, we'll be using relative permeability. For any other medium.
Can you take the previous slide?
Yes. Okay, first note it down, then write the relative permeability.
So what about the pi over here?
Yes, there is one pi. Yes, can I change the slide now? Sure. For any other medium, than free space. If you have any other medium, then you can write your magnetic field as it's mu naught mu r ideal sine theta by r. This mu r here is known as relative permeability. It's known as relative permeability of medium. So mu r is the relative permeability of the medium. That's mu r. Different mediums will have different permeability. Like if in chemistry, you must have heard about diamagnetic, paramagnetic, and ferromagnetic materials, right? So if you have a ferromagnetic material, for ferromagnetic material, your relative permeability is very, very greater than 1. Like for iron, it's around 1000. For iron, mu r is around 1000. But if you take a diamagnetic material, then mu r is small, but it's less than 1. For diamagnetic material, your permeability is less than 1. Permeability is less than 1 means your magnetic field can decrease in a diamagnetic material. Magnetic field will, that means if I take a current carrying wire, I place that current carrying wire in air and I get a magnetic field of 5 Tesla. If I place the same wire in a diamagnetic material, then magnetic field else than 5 Tesla, I can get 0.1 Tesla. In diamagnetic material, magnetic field will decrease. But instead of diamagnetic material, if I choose a ferromagnetic material, then your magnetic field can increase up to 1000. Your field can go up to 1000. You have written it, just note it down. Then we'll see how to decide the direction of magnet. Yes, can I change the slide?
Yes, sir.
Let's change this slide. After Biot Savant, let's write this in vector form. In vector form, we can write Biot Savant's law as dB is mu naught over 4 pi. It's I dl cross r over r cube. This is in vector form. Now you need direction of direction of magnetic field. See, this is the current element. This is carrying current I. This is the small current element, which is dl.
So it's r square r cube.
R cube. Since there's one r in the numerator, so when you open this cross product, it will become r squared. That's dl. You're supposed to calculate magnetic field here. This is r. Now, I need direction of magnetic field. What will be the direction of magnetic field here? For direction of magnetic field, first of all, remember that magnetic field is always perpendicular to r. This will always be perpendicular to your position vector r. And we have various rules to measure to get this direction. Direction of magnetic field. is perpendicular to current element and R, position vector R. It's perpendicular to both current element as well as position vector R, and is given by right hand thumb rule. Right hand thumb rule. Now see how to use right hand thumb rule. There are two ways to use right hand thumb rule. The first is method 1. So method 1 says if you have this wire, take your right hand, hold your wire in this way that your thumb points in the direction of current. Hold this wire in this way so that your point thumbs in the direction of current. This curvature of finger will give the direction of magnetic field. So the method 1 says hold wire in right hand such that thumb points in direction of current. Curvature of finger will point along magnetic field. Curvature of finger will get point along the direction of magnetic field. So just hold the wire in such a way that your thumb is pointing in the direction of current. This curvature of finger will give you the direction of magnetic field. For this, I am showing you an animation. See, for the next 3 chapters, directions are very crucial. You cannot solve these numericals if you don't know direction rules. So it's like 50-50, 50% for formula and 50% for direction. You cannot use formula if you don't know the direction of magnetic field. So I'm showing you few animations. Just give me 1 second. 1 second. Yes. Yes, is it visible?
Yes, sir.
See, this is the wire which is carrying current in upwards direction. So you have to hold this wire in a way that your thumb points in the direction of current. So let's hold this wire in a direction so that your thumb points in the direction of current. This is the curvature. See, the fingers are going, the curvature is going in inwards direction, means this is the direction of magnetic field. If I ask what's the direction of magnetic field here, the direction of magnetic field is inwards here. And we represent inwards with a cross. If I ask what is the direction of magnetic field here, the curvature is going outwards. Hold thumb in this way. Over here, the curvature will go inwards. But for here, the curvature will come outwards. This is the way, na? This is the curvature. This is how it is moving. It goes in, then it goes out. If I ask here, the direction of magnetic field is outwards. This is one simple way to decide the direction of magnetic field. This is inwards and this is outwards. Just simply hold your conductor in such a way that your thumb is in the direction of current. Actually, your curvature will do the rest of the things. Is it clear, this method?
Yes, sir.
Yes, sir.
Everyone? Shazada?
Yes, sir.
Oh, Sania.
Yes, sir.
Sania, you are from the starting. You have joined from the starting of the magnetics or just
No,
now?
just now.
Just now. Okay, you have missed the starting lecture. Anyways, you have missed the formula for the magnetic field, but at least for the direction, take your right hand in such a way that your thumb is in the direction of current. So this curvature of finger will give magnetic field. Here the curvature is going inwards, magnetic field is inwards. Here the magnetic field is outwards. Okay, that's one law.
Yes, sir.
That's law number one. Then we'll discuss law number two. Just note it down. Then we'll see law number two. But whenever you have straight wires, use the simple rule. Just put your thumb in the direction of current, your curvature will give you the direction of magnet. Note it down. Can I change the slide?
Yes, sir.
Yes, sir.
Okay, I'm giving you one simple example. This is the wire. And in this wire, your current is going upwards. I take 2 points, point A and point B. Draw this wire on your copy, on your notebook. Draw this wire and these points on your notebook.
Yes, sir. Done.
Take right hand, put your thumb over the notebook such that your thumb is pointing in the direction of the current. What do you think? Where will be the direction of magnetic field at B over this point? Where is your curvature going? It's inwards, outwards. Where is it going?
Inwards.
Inwards. Outwards.
Inwards?
Inwards.
Outwards.
At B, not at A. B.
Inwards.
Inwards.
Like you just place your thumb here, and if you look at the curvature of your finger, then your curvature of finger would be in the inwards direction.
It's an inwards.
Inwards?
Yes, sir.
At B,
Yes, sir.
inwards. I will represent inwards with this cross. Whenever I draw cross, cross means into the plane, right? At A, see, if your curvature is going inwards at B, then it's obviously will come out from A. So at A, it should be. Is it clear, or I should explain it one more time?
No, sir. It's clear.
Everyone,
Yes, sir. It's clear.
Fatma,
Yes,
Mariam,
sir. Okay. Yes, sir. Yeah.
Sania, it's clear now?
Yes, sir.
Let's do one more example. See, formula is easy. The only issue with magnetics is this direction. Let's take this direction, Sam. Draw it in your notebook. Again, this A and B. Draw it again. And decide what's the direction of magnetic field. Just put your, you can rotate your notebook, right? Or you can rotate your hand. Just place your thumb in the direction of current now and tell me where your curvature is going at B. First, give me the direction of magnetic field at B. Is it inwards again or it's outwards now? Where is it going?
B is outward.
Outwards?
Yes.
Okay. What about the rest, Shazada? Is it going inwards or outwards at B?
So it's going inwards.
Inwards at B again. Okay. You're using right hand or left hand, Shazada?
So right hand.
Right hand. So if you take your right hand, put it in the direction of the current. Current is downwards now. So thumb will go somewhat like this. Like if this is down, then these are the curvature of the finger. So curvature of the finger will rotate like this. It will come out from B, na?
Yeah, so it will come outside.
It's coming outside. See, these directions are very crucial. Just tell me. I will repeat it again. Mariam, what's the direction at B? Inwards, outwards?
Outwards.
Outwards. This is outwards. and here it will be inwards. There is one more method to use right hand thumb rule. That's a bit lengthy, but you should know that method also. Right. And that method is taken from the cross product. That method says place your finger in the direction of first vector, which is DL, and curl it toward the second vector, which is R. Your thumb will give the direction of magnetic. It says this is the cross product rule. Place your finger along the direction of current, that is DL, and curl it towards R. Thumb will give direction of magnetic. Towards R or towards the point, thumb will give the direction of magnetic. This means if this is your current carrying element, this is your DL, and this is your point P, this separation is R. Then do one thing. Take your right hand, draw first of all, note it down. Just note it down. So place your thumb in the direction of current, then curl it towards the point. Your thumb will give the direction of magnetic. Written? Can I change this right now?
Yes, sir.
Yeah. So the law says just draw this in your notebook first. Just draw this in your notebook first. Now, take your right hand, place the finger of your right hand in the direction of current. Place the fingers of right hand in the direction of current. You can place your fingers in two ways. Like some would be placing like this, or some may be placing like this. So try to place your finger in the direction of current in such a way that your palm points towards the point P. That your palm is towards the point P. I'm saying again, take your right hand, place your finger along the direction of current in such a way that your palm is towards the point P. So you placed your finger in this way. Take your right hand, place it along the direction of current. Now curl it towards the point. Curl it towards the point P. Where is your thumb going? Where is your thumb pointing? Inwards, outside, outwards, right,
What?
left? Where is thumb pointing?
Inwards.
Inwards. Inwards. Sania?
Inwards.
Fatma? And be very honest while telling direction. Huh?
Sir,
Fatma?
down, right? Down to the
Downwards.
page. Down the page.
Yeah, that's inwards, into the plane. Huh?
Yeah.
Into the page. Fine. So that's the direction of magnetic field. This is how we use right hand thumb. This is how we use right hand thumb. There is another wrong method also to use right hand thumb rule. Now place your right hand, place your finger in such a way that your fingers are in the direction of current, but now your palm is not towards the point P, it's opposite to the point. This back of your hand is towards the point.
Outwards.
1 second. Can you curl it towards the P? Try to curl it towards the point P. Just tell me, can you curl your finger towards P now?
No, sir, not possible.
Is there anyone who's able to curl its finger towards the point P? Yes. No. Right. Obviously, if you are using your right hand thumb rule in the wrong way, then you cannot, like, I cannot curl my finger in this will break. Huh?
So maybe I
So
can do
maybe you can do.
Abdullah's hand. In
Okay.
Abdullah's
Okay. Okay. On Abdullah's hand. So Abdullah तुम्हारा हाथ तोड़ के रहेगा ये. So that's right hand thumb rule. So if you are using your right hand thumb rule in the wrong way, like if you are placing your finger in the wrong direction, then you cannot curl it towards the point. So just placing is not enough. You have to place in the direction of current and then you have to curl it towards the point. Then your thumb will give the direction of current. I know it's lengthy. This is straight up. This first one is straightforward. But you should know both the rules, both the right hand thumb rule to get the direction of current. Is it clear?
Yes, sir.
Okay. There's one more thing. Throughout magnetics, we'll be using right hand thumb rule and we'll be using this cross product extensively. So I'm again writing some basic rules for cross product. I'm sure that you remember these things, but just for my own satisfaction, I'm writing these rules again. A and B, if I write A cross B, the magnitude of A cross B is AB sine theta. Yes, Noor, I'm just coming to it. So for the second method, just take your right hand, place your finger in the direction of current and curl it towards the point. Your thumb will give the direction of magnetic field. So if you place your finger along DL and curl it towards P, your thumb is going in the direction of magnetic field. If you place your finger in the wrong way, like if you place your finger in this way, then again it's pointing towards the current, but it can't be bended towards the point. It can't curl towards the point. So that's the wrong way of using right hand thumb. Take it along the current and curl it towards the P. So this is how we define A cross B, which is AB sine theta. Next, you will need the cross product of unit vectors. You need cross product of I and J, J and K and I. That you can do in this way. This is I cap. This is J cap. This is K cap. We can write I cross J, J cross K, K cross I. If you're going clockwise, then it's positive. It's positive. But if you're going anti-clockwise, then this is negative. Means I cross J is positive. But J cross I is negative. J cross K is positive. But K cross J is negative. Similarly, it's K cross I is J cap. I cross K is minus of J cap. Is it clear?
Yes, sir.
Yes, sir.
Okay. Always remember these relations. We're using these in numericals. Just note it down. We'll do first numerical on Bart-Switz. Tell me once you have written. Okay. Shazada, can I change the slide?
Yes, sir, done.
First question on Biot-Savart law. So this is solid example of NCRT, and this is x-axis, and this is y-axis. This is your current element here. This is your current element placed at the origin. This is your small current element placed at the origin. This is your current element delta L. Current of 10 ampere is flowing through it along x-axis. This is y-axis. You're supposed to calculate magnetic field at point P, and this point P is, let's say, 10 meter from the origin. Delta L is given as 0.001 meter. So calculate magnetic field at P. Magnetic field at P due to current element at origin. Due to current element at origin. So I'll be solving this numerical by two methods. We'll first solve it in proper vector form, then I will also solve it in scalar form. So first, let's solve it in vector form.
Sir, only one method is okay, right? Or is it?
Anyone is okay. So in vector form, you can write this as delta B is its mu naught over 4 pi, its current I, its delta L, its cross R over R cube. It's mu naught over 4 pi. Now let's substitute all values. So your current I is 10 ampere. Your delta L is 0.001. The direction of current element is same as that of current. Current is going to the right hand along the x-axis. That means direction of current element is along x-axis. Do one thing here. Just write the direction of DL is same as that of current. Write that direction of DL is same as that of current. Direction of current element is exactly same as that of current. Just note it down here. So your current is along x-axis. Your current element is also along x-axis. And what is the unit vector along x-axis, Shazada? Shazada, what is the
Yes,
unit
sir.
vector along x-axis? I, J, K. Which one is along x-axis?
Sir,
I cap. Then we need position vector R, right? So we have I, we have delta L, we need R. What is R? Separation between the current element and the point. That's 10 meter. Fatma, what is the direction of position vector? It's along y-axis. Which unit vector you will use?
J cap.
J cap. So your R will be 10 J cap. Now do one thing. Let's substitute all values here and tell me what's the answer. I think this much of hint should be enough. Just substitute all these values here. You know how to solve these type of cross product. And write the final answer. What's the final answer?
So what's the value of mu zero?
Yeah, yes. Value of mu naught, you should remember. Mu naught is 4 pi into 10 raised power minus 7. Please write answers in chat room. Okay, Noor. Noor, just check your calculation once more. Like you're doing some mistake in power of 10, I guess. Abdullah, you also just check your power of 10. Fatma, you also check your power of 10. No, Emma, just check your power of 10. Huh? No, Sania. Abdullah, it's R cube in the denominator, na? Okay, I'm just one Shazada left and Shazada and Mariam. Answers. And Fatima, yes, Fatima, I've written. No, Fatima. You're close to answer, but not exact. It's not exact. It's better than the last one. But still, it's not the exact answer. Shazada, are you solving it? No.
Yes, sir.
Mariam? Okay. So when I substitute all these values here, what I get is I get delta B is mu naught, which is 4 pi into 10 raised to the power minus 7 over 4 pi. How much is I? I is 10 ampere. How much is delta L? Delta L is, see, this is 0.001. So 10 raised to the power minus 3 I gap. R is 10 J gap. Current is also 10 ampere, na? Over R cube, 10 cube. So 4 pi will cancel this 4 pi. So what we have is 10 raised power minus 7. Just 1 second, huh? Minus 7 over 1 minus 6. So we have 10 raised power minus 7. You're multiplying, this is 10 raised power 1, so power gets added up. Minus 3, this gets added up. Power 1, this gets added up. Divided by 10 raised power 3, this gets subtracted. I cross j. I cross j is k. Minus 7 and this minus 6, yes, minus 11 is right. And ijk is k. Yes, 10 raised power minus 11 is correct. So who was correct? Ahmed is correct. Noor was correct. 10 raised power minus 11 k cap Tesla. Okay, you got the same, but you wrote Abdul. Okay, 0.1 into 10 raised power minus 10. Right, Abdul. Okay. Yes, Ahmed and Noor was correct. This was method 1. You can also solve this. Is it clear now, everyone? Fatma, Sania?
Yes, sir.
Okay. We can solve the same numerical in scalar form also. In scalar form, that's method 2. In scalar form, we write delta B as mu naught by 4 pi. It's ideal sine theta over r square. Or instead of dl, you can write delta L if it is given. Your I is 10 ampere. Your delta L is 10 raised to the power minus 3 meter. Your R is also 10 meter. Theta. See, this is your delta L and this is your R. Now, perpendicular to each other. One is along x-axis, another is along y-axis. So angle is 90 degree. So theta is 90 degree now. When I substitute all values here, I will get delta B is 4 pi into 10 raised to the power minus 7 over 4 pi into current I, which is 10 delta L, which is 10 sine 90 over R square, which is 10 square. 4 pi will cancel this 4 pi and you will get the same answer. Ten raised power minus 3 minus 11 Tesla. But the issue is, if you calculate in scalar form, then you will get only magnitude. You will not get any idea about the direction. You will get only magnitude. For direction, now you have to again apply right-hand thumb. The best thing about vector form is in one step you get both magnitude as well as direction. But in scalar form, you will get only magnitude. Now apply right-hand thumb rule and get the direction. So when you apply right-hand thumb rule, what's the direction of currents along 10 ampere? So take your right hand in a way that your thumb is along the x-axis. So what do you think? Where is the curvature going at point P? The curvature is outwards or it's inwards now? Take your right hand, place this conductor in such a way that thumb is along x-axis. Yes.
Outwards.
Over point P, where is curvature? Out or in?
Outwards.
Inwards.
At point P, see?
Outwards.
Just give me 1 second. Yes. This is x-axis. So my curvature is coming outwards. Huh? Just above the conductor, it's coming outwards if I'm using right hand. Below the conductor, it will go inwards. This is going in this way. Yes. Is there anyone else who is getting inwards at point P?
Me.
Still getting inwards? Okay, just give me 1 second. Just once check once. You're using right hand, na? Take right hand. Place your thumb along positive x-axis, okay? And now see the curvature of the finger. Where the finger is pointing? It's pointing towards you or away from you?
Away from me.
You're using right hand or left hand? Just check once.
Right.
Right. Your thumb is along positive x-axis.
Yes. It's facing the paper.
Either your thumb is towards negative x-axis or using left hand. You're using right hand, right?
Yes, sir.
And thumb is along positive x-axis, definitely. And your fingers are not coming towards you, you're saying. Should not happen.
Yeah, it's towards me.
So what mistake you were doing? You're using left hand.
I curled them.
You? Acha, curled. Okay. It's going outwards. Is there any lefty in this class? Someone who use left hand?
Maria.
Mariam, okay. Wait, Ahmed. Okay. So these lefties have issues with the right hand thumb rule usually. They always use left hand and river. Anyways, so if you use right hand thumb rule, then your fingers are coming outwards. When your fingers are coming outwards, that means it's outwards. When I say outwards, that means out of the plane z-axis. Z-axis means unit vector is k cap. So now you have to multiply with the unit vector to get your answer in vector form. 10 raised to the power minus 11 k cap Tesla. Okay. So that's your choice, which method you want to use. If you want to use vector form, then there are certain issues like you have to convert your delta and r in vector form. But once you get your delta and r in vector form, then you can directly get the direction of magnetic field. You don't have to use right hand thumb rule. But if you are using this in scalar form, then you will need right hand thumb rule to get the direction of current. Clear, everyone?
Yes, sir.
Yes, sir.
Okay, just note it down. We'll stop here. Next class, we'll start applications of Biot-Savart's law.